What you see here looks like an ordinary stone, doesn't it? A gem lying silently beneath the earth for millions of years. It doesn't shine. It doesn't sparkle. Nor does it seem dangerous. But within this stone is hidden one of the most powerful energies humanity has ever discovered. A destructive force in the wrong hands. A power that illuminates cities in the right hands. This raw uranium ore you see is still dormant. But the atoms within it, according to the most fundamental laws of nature, carry immense potential. So how can an ordinary piece of rock become a substance so strategic that it can change global politics? How can a tiny difference at the atomic level create one of the world's most debated technologies? Today, we look behind the scenes of that transformation. A journey that begins in the earth, extends to the laboratory, and descends to the heart of the atomic bomb. Ready? Let's begin. Don't forget to like the videos and subscribe to our science channel to stay informed about scientific content and technologies. Could a city be destroyed with the push of a button? Uranium is under strict control in the international balance. Could the energy hidden within an atom really be that great? What transforms a substance from an ordinary metal into an element that changes global balances? The atomic bomb is forbidden because it's so easy to make. In this video, you will see how uranium enrichment is possible in a simple laboratory, and even in a garage, and the processes leading to bomb making. Uranium is therefore not an ordinary ore. Raw ore alone is not powerful. But when the ratio within the atoms begins to change, that's when the picture changes. The strict controls implemented worldwide, the constant monitoring of nuclear activities, and the fact that some countries' programs have been the subject of debate for years is no coincidence. This is also why the nuclear programs of countries like Iran are on the global agenda. The issue is not just energy production. It is the technological capacity that makes that energy possible. And at the heart of this capacity is the uranium enrichment process. What physical and chemical steps does an ordinary ore extracted from the earth go through to transform into a strategic material? Now, we are entering that process. What if I told you that almost all the uranium on Earth is not the kind used for nuclear energy? In nature, about 99% of uranium is uranium-238. Only a tiny fraction is uranium-235. And yet, that tiny fraction is the one that can sustain a nuclear chain reaction. So how do we increase something that barely exists in the first place? That process is called uranium enrichment. Here's where it gets interesting. Uranium-235 and uranium-238 are chemically identical. You can't separate them using normal chemistry. They react the same way. They look the same. The only real difference? Mass. Uranium-238 is slightly heavier. Uranium-235 is slightly lighter. And that tiny mass difference changes everything. First, uranium ore is processed and purified. Then it is converted into a compound called uranium hexafluoride. Why? Because uranium hexafluoride can become a gas. And gases can be separated based on mass. Once in gas form, it is fed into high-speed centrifuges. These machines spin incredibly fast, creating powerful centrifugal force. Inside the spinning chamber, the heavier molecules drift slightly outward. The lighter ones stay slightly closer to the center. The difference is microscopic, almost insignificant, which means this process must be repeated again and again and again, step by step. The concentration of uranium-235 increases. That's enrichment. a process built on physics, precision engineering, and the smallest difference in mass you can imagine. And what makes it even more fascinating is how such a tiny atomic detail can reshape global energy and geopolitics. This enriched uranium is so sensitive to neutrons that even the smallest neutron particle hitting this material can cause the enriched uranium to explode instantly. You don't want enriched uranium to explode spontaneously. Therefore, enriched uranium pieces are stored in special containers in chambers that absorb neutrons. Here, when the enriched uranium content is between 3 and 10%, it is used in nuclear reactors for energy production. However, to acquire the characteristics of a nuclear weapon, the enriched uranium content must reach at least 80%. This process is both lengthy and requires tons of uranium ore. If the amount of enriched uranium in a nuclear bomb is low, much more uranium is used. This also causes the bomb to become heavier. However, if the amount of enriched uranium is very high, this allows the weapon to be made smaller. The critical mass of highly enriched uranium, at 85%, is approximately 50 kilograms. This means a uranium sphere of about 17 centimeters in diameter at normal density. Quite small. With a higher enrichment rate of uranium, a smaller and smaller diameter explosive uranium can be produced. After this stage, the bomb is prepared. A uranium sphere, rich in the U-235 isotope, is placed in the center of the bomb. After this stage, the triggering mechanism is activated. There are two options. One is chosen according to the bomb's architecture. Option 1, the uranium sphere is bombarded with neutrons using special devices. This process creates a fission chain. This method is preferred for small bombs. If a larger bomb is being prepared, option 2 is preferred. In this method, the uranium sphere is split into two parts. Using conventional chemical explosives, one uranium piece is launched at the other. The collision initiates a fission chain. Fission is the splitting of large atoms into smaller atoms. This event has byproducts, a tremendous amount of heat, radiation, and neutrons. Heat and radiation are the purpose of the bomb. But what about the neutrons? Each U-235 atom produces 3 neutrons upon fission. These neutrons collide with neighboring U-235 atoms, causing another 3 neutrons to be produced there. Heat and neutrons. Heat and neutrons. And more. These reactions continue in this way. That's why this process is called a fission chain. This process occurs so quickly that all the uranium is converted into energy within seconds. And then, the Big Bang. What does it actually take for a nuclear chain reaction to happen? Is it just about having uranium U-235? Or is there something more precise? More fragile? More conditional? Here's the truth. A nuclear chain reaction does not start just because fissile material exists. It starts only when several physical conditions line up perfectly. Condition number 1. Fissile atoms must be close enough together. When a fissile nucleus splits, it releases energy. And more importantly, it releases neutrons. Those neutrons must hit other fissile nuclei before escaping the material. If too many neutrons escape, the reaction fades out. No chain reaction. Condition number 2. The right geometry. Shape matters. Because neutrons travel in straight lines. In certain shapes, they are more likely to remain inside the material. In others, they escape easily. Small change in geometry. Big change in behavior. Condition number 3. Sufficient density. When atoms are packed more tightly together, neutrons have a higher probability of colliding with another nucleus instead of flying away. Distance at the atomic scale determines everything. Condition number 4. Neutron balance. For a chain reaction to sustain itself, each fission event must, on average, cause at least one more fission event. Not zero. At least one. This balance is described by a factor physicists call the multiplication factor. If it's below a certain threshold, the reaction dies out. That's why nuclear bombs are engineered with extraordinary precision. Now do you understand why uranium ore is under very strict control in international markets? Why uranium enrichment processes are not wanted by other countries? Because, as you can see, making an atomic bomb is a very easy process, with simple laboratory equipment, and with setups that can be built in a garage. Uranium enrichment is easily possible. Don't forget to subscribe to our scientific channel and like the videos to stay informed about similar videos. See you in the next video.